Hello and welcome to this second session. So you remember from the first session we derived this hydrogen energy formula that we see on the screen, and we did this from really starting from some very basic physics formulae, the electrostatic force, the centripetal force, equating these, then quantizing the angular momentum, and ultimately deriving expressions for the kinetic energy and the potential energy of the electron, and then summing these up to give the total energy. And so you can see in this formula here the hydrogen energy there is equal to a half of the potential energy. And the reason for this is that we found that the kinetic energy was equal to minus half of the potential energy. And so when you sum the kinetic energy and the potential energy to get the total energy equals then half of the potential energy. And so from that expression, which looks like the potential energy, we then were able to equate r, the distance of the electron from the nucleus, to n squared, the quantum number we introduced when we quantized angular momentum, multiplied by the Bohr radius, a0, divided by the proton number. And so when we substitute that expression for r in to the hydrogen energy formula, we get this more complicated looking expression. And it's at this point we tend to introduce the so-called Rydberg constant. And so the Rydberg constant is just equal to the ionization energy of hydrogen, 1312 kilojoules per mole, often written as 13.6 electron volts by physicists, and this is half a Hartree. And so below that we write here the total energy of the hydrogen electron in this simplified way, either in terms of Rydbergs or in terms of Hartree. And you can see in both of those expressions the energy is negative. And this is because we define the zero energy as when the electron is free from the nucleus. And so obviously when the electron is bound by the nucleus, we need to put energy in to get the energy of the electron up to that zero level. And so Z here, the proton number, and of course up till now we've just been considering Z equals 1, the hydrogen case, but you can have hydrogenic atoms for heavier elements, helium plus, lithium 2 plus, etc. And this is simply where you've ionized off all the other electrons, so there's only one electron left. And so we're going to consider now some of these other hydrogenic atoms. So there's a problem here calculating the ionization energy of these hydrogenic atoms. So yeah, lithium 2 plus, so obviously lithium is atomic number 3, normally got 3 electrons. If we start off with lithium 2 plus, there's only 1 electron left. Beryllium 3 plus, same sort of thing. Copper 28 plus. So yeah, this was the highest value of Z I could find, the ionization for the 1 electron ion. Now obviously copper 28 plus is not exactly familiar chemistry, but in fact we can create these species when they're sort of highly excited in the gas phase. So it is possible to collect data on them. And so a bit lower down I've got the actual data that I looked up, and these are in that electron volt unit. So the constants beneath here show you how to convert the electron volts into the Hartree. So obviously a volt is defined as a joule per coulomb of charge. The E there, that's the fundamental unit of charge, that very small number times 10 to the minus 19. Then we've got the Avogadro constant there to convert it into a molar quantity, and then to convert kilojoules per mole into Hartree, the atomic unit, we're dividing traditionally by 2625.5. So using those constants for the conversions, using our equation for the ionization energy of a hydrogenic atom, we can now calculate what we think those ionization energies ought to be and compare them with the actually experimentally determined ones. And so that's the exercise. And then you're asked, when you calculate these energies and compare them to the experimental ones, are they good approximations? Is the equation a good approximation? So what you might like to do is pause this now, have a go, and then I'll show you the solutions in just a second. Right, now here are the solutions. So the ionization energy of these species is just this very simple expression, half z squared divided by n squared. And of course n is 1 in all these cases because there's only one electron, so it's in the first shell. So we can kind of forget about that n really. So very straightforward calculation in atomic units there. And then we string these constants together to get a conversion factor for electron volts into Hartrees, and then apply that to the databook values, and we see this absolutely phenomenal agreement. So for example with lithium 2+, there you go, you've got a 4 significant figure agreement there with the theoretical one. The beryllium 3+ is nearly as good, and then when you get to copper 28+, the agreement's not quite so good there, but it's still only about 1% off, so it's still remarkably close. So really, again, this is phenomenal how such a simple, naive-looking equation like we've got is giving us phenomenal accuracy with our predictions. So it just goes to show that our calculation of the hydrogen ionization energy, which again was absolutely spot on, wasn't just a one-off. For any one electron system like this, our predictions with this very simple theory are extremely accurate. So just trying to really emphasize that point with all these different hydrogenic atoms. But then it's also quite an interesting discussion about why might it be that for heavier elements the theory just breaks down a tiny bit, just gets slightly less good. What could it be about the higher proton numbers that lead to a bit of a deviation from the predicted energy? So it's quite revealing if we look at the speed of the electron. So last time we got an expression for the speed of the electron from our angular momentum expression. We can substitute that into the equation before we had for the distance of the electron from the nucleus, and that gives us this expression here for the speed of the electron. And it so happens that we can make some useful progress if we substitute into this expression the so-called fine structure constant. So I'll talk a little bit more about this later. But it's this quantity e squared over 4 pi epsilon naught h bar c. It's actually quite a famous constant given the symbol alpha. And if we substitute this in to our velocity expression, we get a very simple expression here where the velocity of the electron equals c, that's the speed of light, times alpha, this is the fine structure constant, multiplied by the proton number z divided by n. So again, n equals 1, so you can sort of forget about that. And interestingly, the fine structure constant takes this value 1 over 137. It's just a dimensionless number there. And so when we look at the equation for the speed, we see then that the speed of the electron is just directly proportional to z, the atomic number, because c and alpha are constants. And also looking at the magnitude of alpha there, we can see that for heavier atoms, the speed of the electron is going to start approaching the speed of light. So in fact, if it obviously the periodic table goes up to element number 118 at the moment, so we don't go any further than that, but you know, if we were to have element number 137, this equation would predict a serious problem, because if z was 137 and if alpha is 1 over 137, that predicts that the speed of the electron would be the speed of light. And this isn't allowed. You can't have particles being accelerated to the speed of light. Only light can go the speed of light. And so I suppose the fact that we don't have any stable elements above 118 means this isn't actually a problem for us, but it's an interesting thing. But the fact that these 1s electrons can go to speeds approaching light actually has some quite interesting implications, and we can explore a couple of these now. But just before we get onto that, a little bit more about the fine structure constant. When you look at this expression for the fine structure constant, e squared over 4 pi epsilon naught, we recognise that from our potential energy expression. That was that minus ze squared over 4 pi epsilon naught r. So actually, if you make e squared over 4 pi epsilon naught the subject, that would be equal to the potential energy multiplied by the distance r. So that tells us that e squared over 4 pi epsilon naught must have the dimensions of energy times distance. So the interesting thing is that there are two other fundamental constants which, when multiplied together, have the dimensions of energy times distance. And these are Planck's constant and the speed of light. So Planck's constant is in units of joule seconds, energy times time, and the speed of light, obviously speed, that's distance divided by time. So when you multiply those together, the time cancels out and you get a quantity which is energy times distance. And so if you take your E squared over 4 pi epsilon naught and divide it by h bar c, then you end up with a quantity where all the units have cancelled, a totally dimensionless quantity. Now, this is interesting because what about atomic units? And so this little exercise, something to think about. What must be the value of the speed of light in atomic units? So you could pause the video, have a little think about that, and then I'll give you the answer. So, about the atomic units. Now, with the fine structure constant, because it's dimensionless, it's independent of whatever units you choose for all the constants, which means similarly in atomic units, the fine structure constant must also be 1 divided by 137. But considering that we define the electric charge as 1 in atomic units, 4 pi epsilon naught as 1 and h bar as 1, then in fact C would have to take the value of about 137 for it to work out. And so in slightly more precise terms, it's 137.036. So it's not exactly 137, but it's pretty close, and so it's usually referred to as 1 over 137. Right, so now going back to our high-speed electrons that we were talking about and how they introduce a few interesting anomalies. So this relates to Einstein's theory of special relativity. And so his theory posits that when particles go very, very fast, start approaching the speed of light, their mass increases. And this is an actual feature of heavy element chemistry. So the electrons start getting heavy. It's called the heavy fermion effect. So their mass goes up. So if you increase mass, then you must also be increasing kinetic energy, half mv squared. But we've already met the idea that the kinetic energy and the potential energy are related, the potential energy being minus twice the kinetic energy. So if the kinetic energy scales up, then the potential energy follows it, using that relationship there. And so actually the total energy, which would be minus kinetic energy, actually then becomes more negative, and this stabilizes the electron. And so that therefore leads to a higher ionization energy than you would have predicted, as we saw before with the copper 28 plus. And we can also think we get a similar answer looking at it in terms of angular momentum. So angular momentum is a conserved quantity, and it's equal to mvr, mass times speed times distance from the nucleus. So for a given velocity, if the mass starts going up because of this effect, in order for angular momentum to be conserved, r, the distance from the nucleus, would have to go down. And so it would follow that these orbits would shrink when the electron speed gets very high because of the mass increase to preserve the angular momentum. And so this causes the electron to kind of shrink in a bit towards the nucleus. And it's interesting because we find at the bottom of the periodic table, the heavy elements, quite a few of the trends that we're used to in chemistry start to go wrong. We see some anomalies creeping in, and very often these are related to these heavy electron effects. So a famous one is the fact that mercury is a liquid. So yeah, not really something we would otherwise have expected. And I think this is related to the fact that the electrons which you would normally expect to be part of the metallic bonding, so those delocalized sea of electrons, if they start becoming more core-like because of the radius decreasing, that, as it were, takes away from the bonding. So by weakening the bonding, this allows the solid to become a liquid, to reduce the forces between the atoms. And various other bizarre things that we see. at the bottom of the periodic table, some sort of slightly odd oxidation numbers, colour of gold arguably as well, some ionisation energies, not what you'd expect. Very often these anomalies can be traced back to this heavy electron phenomenon.